In this section, I'm going to give you an introduction to the concept of vectors and some of the algebra associated with vectors. Vectors are a really important concept, especially in physics. We also see them in later mathematics courses. If you're going to take Calculus 3, we spend a lot of time dealing with them there and in later courses. Okay, so basically, there's two different kinds of physical quantities. They're called scalars and vectors. A scalar is a physical quantity that's completely specified by just a number. For example, length. If we say the length is 7 feet, that's a scalar quantity. The volume is 30 milliliters. That's a scalar quantity. However, other quantities require two concepts, a magnitude and a direction. We call those concepts, those physical quantities, vectors. A couple of quick examples is force. A force has to have a magnitude. Often forces are represented in pounds or newtons. That's a unit of force in the SI unit system. So if I were to say 15 pounds, well, that's a weight. However, if I say 15 pounds in a direction, 15 pounds at an angle of 30 degrees, that is now a force. If I say that the ball is traveling at 60 miles per hour, that's a speed. However, if I give it a direction, the ball is traveling 60 miles per hour northward, now it's a velocity. It has a magnitude and a direction. And so that's the big difference between a scalar quantity and a vector quantity. A vector must have magnitude and direction. So now let's learn a bit about vectors in more detail and how we can deal with them. So first, a little bit about the representation of vectors. If A and B are 2 points in the plane, then the vector from A to B written as AB, and then we put an arrowed line above them. Okay, and the direction of the arrow is important. If the vector is from A to B, then we need to list A, then B, and have the arrowed overhead in that direction. All right, so then the vector AB is the directed line segment with arrowhead at B. So if I said, here's this point A, and here's the point B, then now there's the vector, right? This is the vector AB. It has initial point A and terminal point B. It has a magnitude. Now, if we're drawing a vector in 2 dimensions, we can think of the magnitude as its length, and it has the direction, right? The direction is the direction that the vector is pointing. Now, one thing that's interesting about vectors is that any translation of a vector, if I take the vector and I move it left, right, up, down, it's the same vector. It's equivalent. It's an equivalent vector. So if I take this vector and let me move it over here, that's the same vector, right? It's the same vector. It has the same magnitude and the same direction. It is the same vector. Now, we have a very important translation that we need to be aware of. If we translate the vector so that the initial point is on the origin, we have what's called a standard vector. So if I take this vector and I move it so that, I don't know if I'm going to be able to do this. Yeah, it won't let me move it perfectly. So if I take this vector and I move it so that it starts at the origin, and this is going to be difficult for me to draw by hand. That looks about the same. So this vector, assume it's exactly the same vector, but now it's starting at the origin, and now the terminal point is now some point P in the plane. If we have a vector like this, that the initial points at the origin, we call this a standard vector, and we'll call it OP. Now, if this point has some coordinates x, y, then we can write this standard vector as in this form. So now OP, the OP vector, can be written in the form of a standard vector as bracket x, y. And so notice in this notation with these angled brackets, that's a representation of a vector. So we've now seen two representations of a vector. We've seen the vector as written with an initial point and a terminal point with an arrow above it. Right? So here's a representation of a vector, and here's a similar representation. Right? I've highlighted those two. Another representation of a vector is a standard vector. Standard vector has the initial point at the origin, terminal point somewhere out there, some point x, y, and we can write the standard vector with the angled brackets and listing the terminal point. Okay, so something to be very careful about. And remember that if I write parentheses, this is an ordered pair. Right? If I write parentheses x, y, that's an ordered pair. If I write angled brackets x, y, this is a standard vector with terminal point x, y. So we've got to be careful about the notation we use. Parentheses means ordered pair, angled brackets means standard vector. So here's an example. Suppose we're given the vector AB with initial point 2, -6 and terminal point 8, 2. We wish to write AB as a standard vector. So I'd like for you to maybe try this out on your own. Pause and see if you can figure it out. All right, so let's see. 2, -6 is down here somewhere. Here's A, and that's the point 2, -6. B is 8, 2. It's up here somewhere. So there's the point B, and so here's the vector AB. So remember that for the standard vector, I need to translate this vector. I need to translate AB so that its initial point is the origin. Well, if I translate A so that its initial point is the origin, I would shift it 2 points left, 2 marks left, 2 units left, however you want to think of it, and 6 units up. And so its initial point is now the origin. But I would have to do the same with B. I'd have to move it 2 units left and 6 units up. And that would give me the point, my new point P. Now if I take 8, 2 and I move it 2 left and 6 up, that would give me the point 6, 8. So then here's the vector OP, and so then AB, the AB vector, can be written as the standard vector 6, 8. So in general, if we have the initial point, right, if our initial is some point, let's just call it x1, y1, and my terminal is the point x2, y2, then this can be thought of as the standard vector well, what did we do? I basically subtracted. I took x2 and I subtracted x1. 8 minus 2 is 6. I subtracted the y's. 2 minus negative 6 is 8. So then the standard vector can be written as x2 minus x1, comma, y2 minus y1. And remember that we have to write it in the vector notation, right, as a standard vector with the angled brackets. So now let's work with that same vector some more. Given the vector AB with initial point 2, negative 6 and terminal point 8, 2, find the magnitude of AB. Recall that we can think of the magnitude, if we're thinking in 2 dimensions, the magnitude can be thought of as the length of the vector. So why don't you try that one out on your own? Alright, so here's one way to look at it. Let's take AB, and we now have the standard vector from the previous slide. Right, so I can think of the standard vector AB as this vector, which was, oh gosh, I've forgotten it already. The standard vector was 6, 8. Right, so if this is the point P, and it's 6, 8, right, and there's the vector AB. So if we were to think of this, notice that this sort of builds a right triangle. And this distance is 6, and this distance is 8. So then the distance, the length of the hypotenuse of this triangle would then be the square root of 6 squared plus 8 squared. And that's the square root of 100, which is 10. This distance is 10. So what we could say is the magnitude of the vector AB is 10. Now we have a notation for the magnitude of the vector. We'll think of it as, in a sense, it's like an absolute value. If you think of the absolute value in 1 dimension, it was a distance from 0. The magnitude in 2 dimensions is still a distance from 0, but we find it a little differently. So a notation that we'll use is the magnitude of AB will look like this. So we'll put the absolute value bars around the vector, and so the magnitude of AB is 10. Just want to mention that some textbooks use a slightly different notation for magnitude. Some textbooks would write this with double vertical bars. We will use just the single vertical bars. Alright, and so can we generalize this idea? Of course, right? If we have some vector, which is given in the standard vector as a comma b, or x comma y. Let's use x comma y. If we have a vector, it's written in the standard form as x comma y, then the magnitude of the vector is equal to the square root of x squared plus y squared. It's basically just the Pythagorean theorem, just a special notation for it, that's all. Now vectors can be added. Suppose we have two vectors, the u vector, which is 2, 3, and the v vector, which is 5, 1. What does u plus v mean? All right, well, let's draw this out. Let's see what this means. All right, so I've got the u vector, which is 2, 3. Let me put some scale here. There's 5, There's 10. There's 5. There's 10. All right, so the u vector is 2, 3. All right, so here's the u vector. The v vector is 5, 1. V vector is 5, 1. All right, so that's the v vector. All right, so what does u plus v mean? Addition of vectors says basically, take the 1 vector, in this case I'll take the v vector, and move its initial point to the terminal point of the other vector. So I'm going to take this v vector and I'm going to translate it so that its initial point was at the terminal point of u. And so then it would look like, so let's move it here. So there's the v vector again. I've translated the v vector. And so then u plus v in purple is this vector. There's the u vector plus the v vector, which I've drawn in purple. And notice that u plus v vector, it appears to be, if I've drawn this reasonably well, it appears to be the vector 7, 1, which is simply the sum of the a components plus the sum of the b components. So in general, we are allowed to add vectors algebraically if u is the vector x1, y1, and v is the vector x2, y2, then a u vector plus v vector, we simply add the components. x1 plus x2, y1 plus y2. And again, that's a vector. If we add two vectors, then the sum is a new vector, and we add the components. There's one more important algebraic consideration at this time. And that is, what happens if we take a vector and we multiply it by just a number, a scalar? So if I have again the vector u, which is 2, 3, and so 2, 3, I'm just going to sort of freehand it here. So here's the vector 2, 3. What does the vector 4u vector mean, and how would we express it? Well, if we think of what we learned in the past as a multiplication as a repeated addition, this means, in a sense, take the u vector and add on multiple u vectors. And so then 4u vector would look roughly like this. I'm sort of, again, freehanding. There's 4u vector. It would be a vector in the same direction as u, and all we're doing is we're changing the scale of the vector. Instead of it being the original length, we're making it 4 times as long. Algebraically, 4u vector, if we think of this as, again, a repeated addition, this would be 4 times 2, 4 times 3. And so 4u vector would be 8, 12. And so then the terminal point on this 4u vector would be the point 8, 12. And again, in general, if we have some vector u which is given as x, y, then k u vector is equal to kx, ky, where k is a real number, a scalar, not another vector. Vector multiplication is something different. In fact, there's two different kinds of vector multiplication that you'll become aware of. One called the dot product and one called the cross product. We'll worry about those in later courses. Alright, so again, let's look at some generalizations. Let's recap some of the things we've learned. In general, for the u vector, which is given as the standard vector AB, and the v vector, which is the standard vector CD, the magnitude, another name for the magnitude is the norm. Just a name. The magnitude or norm of u vector, written with the vertical bars, right, vertical bars around the u vector, that would be given as the square root of a squared plus b squared, and as the length of the standard vector associated with u vector. Vector addition. U vector plus v vector is the standard vector a plus c, b plus d. We add the components respectively. Scalar multiplication. If we take a vector, standard vector, and we multiply it by a scalar, we multiply the components respectively. Alright, so now it's just some practice with the notation. Here I've given you two vectors, u, which is the standard vector 2, -7, and v, which is the standard vector -3, -4. And what I'd like for you to do is find these various quantities. And so you really should pause and try these out on your own before I do them. Alright, so first, magnitude of the u vector, the norm of the u vector. This would be equal to the square root of 2 squared plus -7 squared. So that's the square root of 4 plus 49. That's the square root of 53. That's fine. Leave it like that, the square root of 53. Similarly, the magnitude of the v vector would be the square root of -3 squared plus -4 squared. That's the square root of 9 plus 16. That's the square root of 25. Now this one I can simplify as just simply 5. U plus v. That would be the standard vector 2 plus -3, comma, -7 plus -4. And so that would be the standard vector -1, -11. U minus v. Now we didn't talk about subtraction. Fortunately, these behave like numbers, in that I can think of this as the u vector plus -1 v vector. Subtraction's addition of the opposite. So then that's u vector, that's 2, -7, plus, now -1 times v would be -1 times -3, comma, -1 times -4. And so then that's 2, -7, plus 3, 4, which is the vector 5, -3. So that was a lot of work to show that basically, if we're subtracting vectors, you subtract the components respectively. 2 subtract -3 is 5. -4 subtract -7 subtract -4 is -3. And so then 2u vector minus 4v vector, well, that would be, let's see, 2u vectors. That would be 4 negative 28. Oh, sorry, I was thinking incorrectly. I multiplied the second component by 4. 2 times 2 is 4. 2 times negative 7 is negative 14. And to that, we will add negative 4 v vector. Negative 4 times negative 3 is 12. Negative 4 times negative 4 is 16. Adding the components now, that's 16, 2. So 2 u vectors minus 4 v vectors is 16, 2. So that's the basic arithmetic of vectors. That's how we add them, scale them, and how we find what's called the magnitude or the norm of the vector. Now we're going to focus on a special type of vector, something that's called a unit vector. So a unit vector is something that has magnitude 1. So a vector has some magnitude, but a unit vector is going to be in the same direction but have a magnitude of 1. So, for example, if here's some vector u, actually let me change the notation here. Here's some vector m, and let's say it has a magnitude of m. So there's a vector m, and the magnitude of m is 10. So if the length of this is 10, then what I want is a v vector that's in the same direction but has a magnitude of 1. So in a sense, what I want is I want to figure out this vector right here. I want to figure out this v vector where the magnitude of the v vector is exactly 1. Well, if we just sort of think about what we've learned in the past, this is just a scaling. All I need to do is figure out 1/10. So in this case, v, the v vector, would be 1/10 of the m vector. So in general, if v is a non-zero vector, then a unit vector in the same direction of v is like this. The unit vector, right, v, and I'll put a little notation here, the unit vector would be 1 over the magnitude of the v vector. Now remember, the magnitude of the v vector is a scalar, so 1 over the magnitude is again a scalar. 1 over v vector multiplied by the v vector. So if I take 1 over the magnitude and I multiply it by the vector, that gives me a unit vector in the same direction as the v vector. So for example, let's suppose then that my new vector m is 3, 4. Determine a unit vector in the same direction as m. Alright, well, I can easily show that the magnitude of the m vector is the square root of 9 plus 16. That's the square root of 25, which is 5. So therefore, a unit vector in the same direction as m, I'll write this as m unit vector, would be 1/5 of the m vector. That would be 1/5 of 3, 4, which would be then 3/5, 4/5. And we can verify that this is a unit vector. Let's verify this. Let's note that the magnitude of the m unit vector would be then the square root of 3/5 squared plus 4/5 squared. So that's the square root of 9/25 plus 16 25ths. And so then that's the square root of 25 25ths, which is, of course, 1. So it is a unit vector, and it is in the same direction as the original vector because it is just a scalar multiple of the original vector. All right, so to find a unit vector in the same direction as a given vector, take 1 over the magnitude of the vector and multiply it by the original vector. So there are two special unit vectors. The vectors 1, 0 and 0, 1 are special unit vectors. And if we were to think of those graphically, if we were to draw our axes, the I vector, 1, 0, is the vector that goes in the horizontal direction exactly 1 unit. And the j vector is the vector in the positive vertical direction and is exactly and has magnitude 1 unit. So these are important vectors because it turns out that I can take any general vector and I can write it as a combination of these two vectors. So let's take, for example, suppose I have a vector AB. Notice that AB can be written as the sum of the vectors A, 0 plus 0, B. Well, then notice that I can then think of that as A times the vector 1, 0 plus B times the vector 0, 1. Thinking of how we multiply a vector by a scalar and just take that backwards. Well, 1, 0 is the I vector, 0, 1 is the j vector, so this is the same as A, I vector, plus B, j vector. So any arbitrary vector can be written as what we call a linear combination of I and j. And that becomes important later on in some problem solving. All right, so here's again some more practice. I want you to try to go through these on your own first before I do them. Given two vectors, u and v, here's some exercises based on those vectors. All right, so first, so u is the standard vector 3, negative 5. V is the standard vector negative 2, 9. Write u and v in terms of I and j. All right, well, u, using what we saw in the previous slide, u, since it's the standard vector 3, negative 5, is the same as 3i vector minus 5j vector. Similarly, the v vector is negative 2i vector plus 9j vector. All right, so from now on, if I say I and j, let's assume that they are vectors and not, so I won't say vector. I'll just say I and j. Express u plus v in terms of I and j. All right, well, if u is 3, negative 5 and v is negative 2, 9, we know how to add them, right? We already know how to add them, and so then we're just going to add them, add the components. Well, if we have them expressed in terms of i's and j's, we still just add the components. U plus v vector would simply be 3 plus negative 2, that's 1i, negative 5 plus 9 plus 4j. Now we do have to write the vector notation. Similarly, u minus v, u vector minus v vector, we subtract the components. 3 subtract negative 2, right? So u minus v would be equal to 3 minus negative 2, that's 5i, negative 5 minus 9, minus 14j. express 2u minus 3v in terms of I and j. All right, so let's see, this one's a little bit tougher, a little bit more work. So let's see, 2u vector, that would be 6, comma, negative 10. And then minus 3v, that's plus negative 3v, 6, negative 27. And so then in terms of i's and j's, 6 plus 6, that's 12 i's, and negative 37 j's. I want to do one more exercise that I forgot to put on here. So part E. I want you to write a unit vector in the same direction as V. All right, so again, that would be a good time to pause. Try that one out on your own. A unit vector in the same direction as V. All right, so we saw this on the previous slide. All right, so V unit vector, that would be 1 over the magnitude of V times, let's not use that notation, that means something else, multiplied by the V vector. All right, so magnitude of V would be the square root of 53. I think we've used this vector before. So that would be 1 over the square root of 53 times the V vector, which is negative 2, 9. And so then that would be the vector negative 2 over root 53, comma, 9 over root 53. All right, so that concludes this section on the algebra that we need to know about vectors at this point. All right, in the next topic, we'll see some actual applications of vectors.